So in this video, I'm gonna quickly go over this code and mainly explain these two functions. The first one is analogWrite and the second was is delay function. So let's first come to the analogWrite. What does this do? So if we see Arduino board, so we can see there are multiple pins. So all these pins are by default for taking inputs, but we can also utilize this or command this to behave as output. So analogWrite is a function that instructs one of the pin to behave as output. For example, here we are interested to command this number 9 pin to act as an output. So that's why we have put this, which is basically pin 9, in the first placeholder under this analogWrite function, and basically saying that port 9 behave as an output. And then what does this second placeholder indicate? So the second placeholder is associated with the voltage that we supply to this pin. So ideally, here for this Arduino Uno, we can see that the voltage supply is 5 volt. So 5 volt is associated with a number 255. So if we put 255, it means it's gonna supply 5 volt. However, if we use 0 here, it means it would supply 0 volt on pin 9. So here we can see 255 corresponds to 5 volt. So what should actually 200 represent? Apparently, from simple calculation, we can see that if 255 is 5 volt, 200 is 3.92 volt. So we might actually intuitively assume that this line of code or this function is actually sending 3.92 volt to port 9. But this is not actually the case, because it works a little bit differently. So how PWM works, for that we have to understand the PWM itself. So on this Arduino board, we can see there are multiple pins, but there are only these pins 3, 5, 6, 9, 10, 11. These pins has a tilde sign before them, and these are only the PW capable pins, and the other are not PW capable pins. So PW capable pins are those pins that can work and send a PWM signal. So a normal signal, for a normal signal, say 13, this is not a PW pin. If we use 13 here, it would actually work like a digital write function, where for the whole duty cycle, the voltage stays as 5 volt. So even though we provide 200 to analogWrite, it will behave like a digital write led pin, comma, high, or it will provide a full signal for the whole duty cycle. But when we are using the analogWrite with one of the PWM capable signal, it is able to provide a PWM signal. So what does it mean? It means this. If we see this picture, so if T is the whole duty cycle, for a certain portion of it, the signal is gonna be high, and for a certain portion it's gonna be low. So even though 3.92 counts as a very intuitive input voltage, it actually doesn't do that way. It toggles, not toggles, it first stays 5 volt and at the for a certain time, and after that it goes back to 0. So again, this thing, like when we are writing analogWrite led pin 200, this 200 is correspond to this plot where the signal stays on high for a certain time and then goes to low for the rest of the time. So it's never in between. It's never in between. So now the next question comes, how can we actually say how much time it stays high and how much time it stays low? The answer is yes, we can do that, and the value 200 is actually used to calculate that. So from here, the time that it stays on high value is this 200 divided by the total time duty cycle T is here over the 255, which corresponds to total duty cycle or total voltage, whatever, and it provides a 0.75 T for 78 T. So for 78% of time or the duty cycle, it's gonna stay high, and for the rest of the time it's gonna stay low, which is 22%. So it's never gonna be in between like 3.75 3.92 volt. It's never gonna be like that. Now we can actually calculate the exact value of how long it's staying for microcontrollers. For example, for 80 mega 328P PWM frequency is 490 Hertz, which is for most of the PWM pins, and then from there we can calculate the duty cycle, which is 2.04, and we can calculate how much time it stays as high and how much time it stays on low. So we can basically calculate that just from the PWM frequency of the microcontroller. Now, if it stays on either high and low, like as I said, that this one would cause the input value to stay on either 5 volt or to 5 volt or to 0 volt. So now with this point 0.9, if I connect a resistor and then an LED and then connect it back to the ground, it should create a circuit, and this LED should receive this signal. Technically, when it's sending 5 volt, it should be full bright or light to the fullest. We should get a brightest form, and then when it basically for 78% of the time, and then when it changes the signal and goes to 0 volt, this would send 0 volt here, and that there will be no signal and there will be no light, so it will be turned off. So that's what we should expect. But what happens, the whole thing happens very fast. So as we can see, this is 2.02 millisecond. 2.02 millisecond is very small. Like for our perception of a thing, like two events occurring one after another, the time interval between two events has to be more than 1/30 second. Below that, we cannot actually see anything. So instead of seeing this LED to first being on to with the brightest light and then getting turned off, what we actually see is kind of the average of these two. So we actually see this light is not very bright, it's kind of dim, and that basically confuses us. So many cases we can assume that probably this is because there is less voltage and that's why the voltage is that's why it's not so bright. But this is wrong. This is just because our error, which is the persistence of our eyesight. Now let's come to the next function, which is the delay function. The delay function, what does it actually do? The delay function pauses the CPU for here 1000. So the delay function pauses the CPU for 100 millisecond or 1 second. So what does it mean by pauses the CPU, and what actually happens when it pauses the CPU? So first what is the CPU? The CPU here is this microcontroller itself. So as we see, this microcontroller itself is the CPU, and when we use the delay function after that, just think about this. So first, here in this page, when we have this analogWrite signal, the program passes from top to bottom. So first it will come to this one, it will execute it. As it executes, we come here. First it will be 5 volt, the LED will turn on, and next it will go right into here to 0 volt, so it will be turned off. So at that point, when we go back to here and ask the CPU to pause, the CPU is not working, then technically it might seem that what we should see the LED being turned off for 1 second. But in real, that is not the case. In real, we will see that it stays like that. Now, this might seem confusing, but there is a reason behind that. The reason is this. So here, let's see, the CPU has two different type of things inside it. The first one is the software, which are basically software control, and the second one are hardware controls. The softwares could be calculations, functions called commands. So when the CPU stops, so when we call the delay function, it basically stops this right away. So when the CPU stops, this delay function will stop this, like will tell this stop all the calculation, and then this will stop this software portion immediately. So this is not running. But there is a second part, which is the hardware portion. For example, timers, PWM generator, UART, serial, ADC, and input-output register. All these things are hardware. So these work a little bit differently. How this works? So when we call the delay function, it definitely asks this CPU to stop, but it doesn't actually impact this. So this hardware, once these are configured, they keep running until a new program is received. So even though the CPU, the software inside that, or all the calculation is paused for 1 second, this thing would take the downloaded program inside that and keep running. And that's why, even though when we are calling the delay function after the analogWrite, we keep seeing this being like that, not like that. So that's how the analogWrite and the delay function works.